Welcome to a quick summary of Lecture 8. So today we're going to introduce the definition and properties of determinants, and then be able to compute determinants using row operations. Determinant will always be labeled det. So, as a recollection, recall that for 2 by 2 matrices, det A is also written as size of A. It's a sign size, or ABCD, where A is ABCD, is AD minus BC, and is the area of the transformation of the unit square. So we have that the proportional change in area that's the determinant. So the general definition for an n by n matrix, the determinant of A also written det A, or size of A, and so on, is the multiplicative change in volume associated to the matrix transformation of A. So you can see my lecture notes for some of the more motivational reasoning in the 2 by 2 case about the properties of determinants. Hopefully they were clear during class. So for now, let me just write down the properties. And there were, if you recall, there were 5 of them. So A is invertible if and only if determinant of A is non-zero. And the reason for this was because the volume doesn't get crushed down when you under the matrix transformation. Number 2, for diagonal or upper or lower triangular matrices, the determinant is just the product of the diagonal elements. Number 3, for a composition, when you change the volume twice, the overall change is the product of those changes. And we had some conclusions from this one. In particular, the det BA, which must be det B times det A, is the same thing as det AB. And moreover, if A is invertible, by considering A inverse is equal to the identity, then the determinant of the inverse is equal to 1 over the determinant. For property 4, under rescaling, det of lambda times A for any scalar lambda is equal to lambda to the n det A. And finally, we saw an example of this during lecture. The determinant of A transpose is equal to the determinant of A. So that was the first section. The second section that we covered was on computing determinant by row operations. Remember, you can always pause this video or rewind if you want more information. You should also check the lecture notes online. So in this case, let me give you the full content from the lecture. So we have 3 different types of row operations. So these are the elementary row operations. What happens in the 2 by 2 case, the picture associated to it, and the general effect. So that's the n by n case. So the first row operation is that some row gets multiplied to a scalar non-zero scalar times row I. Note by fact 5, as a remark, because the transpose determinant is the same as the original determinant, you can also use column operations. In this first case, when I multiply one row, let's say that our 2 by 2 matrix is 1, 0, 0, 2, and we multiply the first row by 3. So the picture is, so the output of the unit square is this 1 by 2 rectangle with area 2, and the new one is the one that has area 6. So the general effect is that the determinant gets scaled by that same multiple. Secondly, we can add one row to another. So in this case, let's pick the same one and add row 1 to row 2. So pictorially, we start off with the same. But now, in the new case, the new output is 1, 1, and the other one stays as 0, 2. You see that the area remains the same, so that the determinant is unchanged. And number 3, we can swap 2 rows. And what happens here, let's do it in this case. And we change from our previous square, which was oriented this way, because the first vector is 0, 1, and the second one is the first one is 1, 0, and the second one is 0, 2. This gets changed to the first one being 0, 1, and the second one being 2, 0. And the orientation is now this way, first and second. So you see that there's a change in the orientation, and so the determinant, let's just check, this is determinant 2, and this has determinant 0, minus 2. So the general case is the same. Determinant becomes multiplied by minus 1. Finally, let me give one example. As we did in class, for a equals 0, 1, 5, 3, minus 6, 9, 2, 6, 1. So then det A is equal to, well, I'm going to change row 1 and row 2. 3 minus 6, 9, 0, 1, 5. And therefore, this picks up a minus sign. And the other line doesn't change. It's the same. And now, because this row 1 has a common factor of 3, I can take that out of the determinant using rule 1. This is equal to minus 3, 1, minus 2, 3. The others are unchanged. And this continues. Notice that the factor I get out is 3 here, because the idea is that if I change this one to that one, I multiply everything by 3. So for the next step, I noticed that I can kill off this term. I'm using Gaussian elimination. So if I add, minus 2 of this row to this one, I get and then I can take out the similar common factor of 5. And this now equals minus 15 using Gaussian elimination again. So this from this. So row 3 becomes row 3 minus 2 row 2. And now this is in upper triangular form, so I can just read off the determinants minus 15 times 1 times 1 times minus 11. Which equals 165, because this is in upper triangular form. That's using property number 2 from earlier.